Player Garbage Collection was presented as part of the Flash in the City conference. This presentation was originally recorded on June 11, 2011, in New York City.
Good morning. Thank you very much. I'm going to make this very difficult on the camera guy. Not intentionally so, but I pace a lot when we talk. So we're going to talk about garbage collection. But we're going to talk about garbage collection probably at a different level than most of the time when it's been talked about before. I plan on talking about it at a pretty low level, what's actually happening inside the player and why, what's happening. So if you're interested in that, stay. If you're not, I won't be offended if you leave. However, I will reserve the right to make fun of you as you walk out the door. In the meantime, who the hell am I? I'm Mike Labriola. I'm a consultant at Digital Primates, the actual architect for Flex Unit 4 as well as the Spoon project, which if any of you are familiar with is the open source initiative behind Flex. I'm a mentor. I architect worldwide applications, and I'm a big fan of disassembling things. My background is actually embedded systems. So I come from a world which is mainly about embedded stuff, very small microcontrollers and processors. I came to Flash, quite frankly, because I wanted something completely different. But sometimes we have that whole nature thing, and we go back to what we actually like. And in my case, I actually slowly migrated back to trying to take apart Flash Player and understand the internals of what's actually happening there. So what are we covering today? We're going to talk about garbage collection as it exists today. We're also going to talk about just a tiny bit, a small bit, of maybe what's coming soon. Particularly that there are some changes. And I don't know that we'll get to all of these, but that's okay. We could talk about them later. Incidentally, open invitation. Anybody that's here that wants to actually sit down and talk about this stuff later with me, I'm at the conference. Find me, sit down, and I'll geek on this as long as you want to. But there's some tiny things coming. They're changing. Number one, in Flash Incubator, there's actually some new APIs that exist for garbage collection that didn't exist before. And if you're a really big geek and watch Tamarin. Everyone know what Tamarin is? Okay. For those of you who don't, Tamarin is the open source, let's call it the engine behind ActionScript that was given to the Mozilla Foundation. If you actually watch the Tamarin repositories, which there's still a lot of work done, there's actually a whole bunch of new garbage collection stuff that seems to be being worked on presently. So there's probably some interesting changes coming in the future onto that front. So we'll talk about both of those and kind of see where we're at. So diving right in. First thing we have to understand in order to get any sort of sense about what garbage collection is about is that we need to understand the difference between a stack and a heap. Does everybody understand what that is? Well, let me go the other way. Who doesn't feel comfortable with the difference between stack and heap? And tell me now. Okay, good. We have two different types of memory we're commonly working with. This is very important for us inside of any programming environment. There's what we call stack and heap. Stack memory is very local memory. So we create a new function. Inside the function, we say var x:'int. That's created on the stack. It's created on this little temporary, transient memory that we use for a function. Okay, it's very simple and very temporary. No big things go on the stack. No things that have global scope or reference go on the stack. Those things end up on the heap. So as soon as we use the word new, as soon as we say, hey, this is a new object, this is a new data grid, or this is a new whatever, we can start thinking about those things as being on the heap. You can think of the heap as just this giant chunk of more or less global memory that sits out there where all of these things are allocated from. Now, there's two different problems here in that stack is very temporary memory and it may have references to things on the heap. In other words, we might have an O:object, which exists in our stack, which has a reference to something that lives out here on the heap. So these two are interrelated, okay? Stack memory tends to be a bit faster. And how we're accessing things. And stacks are very significantly used in the course of development. In fact, if we think about it a little bit, or if we understand a little bit more, when we call a function whatsoever, we're actually using stack memory. So let's say that we call a function that takes two parameters, right, an x and a y. What actually happens in the low-level opcodes, or what happens inside of a virtual machine, or any machine, is that we push what we're about to use as arguments onto the stack. So we have an x and a y, we push that x and a y onto the stack, and then we call our function. And then our function actually pulls those back off the stack. So we tend to think about things at a high level, right? We tend to think about functions and having arguments. But at a low level, there has to be some way that Flash Player routes the two things we just put on, and we said, hey, this is my value for x and this is my value for y, to the function we're going to call. And that methodology is the stack. All right? So we push things onto the stack. We call a function, which really means, incidentally, that all we do is we take a little reference that tells where we're at in our program, and we move it to where the function is that we want to call. And that function yanks these things back off of the stack and then uses them locally. And then when it needs to, if it needs to return something, it pushes that thing back onto the stack again when it's all done. And then it goes back to where it was in the program, and then you yank that value back off the stack. So this stack gets exercised constantly. And the appropriate ways to explain this are being pushed and popped. When we push something onto the stack, it means we throw one more thing on here. And a stack, by the way, is a data structure that piles up, okay? First in, last out, meaning that we call our first method, and if that one calls another one, it gets on top of that. And if it calls another one, another one. So the stack keeps getting deeper, and we keep piling more and more things on top of it. Every time we do something or we get rid of an argument, we pop the stack, meaning the stack gets smaller again. So our stack kind of increases and decreases as we go along. To that end, that's what we get to something called a stack overflow. And most likely people have seen this when we actually wrote something accidentally recursive. We have a function that calls the same itself over and over again. Well, the reason that it's a stack overflow doesn't really have anything to do with recursion, but what it really means is that there's nothing left in the stack space. We've pushed something on, we've called a function, and we push something on, we call a function. So if we have something that calls itself, right? We push it on, we call it, 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 and eventually we're out of space that's been allocated for this stack. There's nothing left. That's a stack overflow, okay? Not just a site where we can ask questions. It's a stack overflow. It's when something actually has gone completely wrong and there's no way we can recover from it. We can't recover because of the fact that at that point, we don't have any way to get back to where we were because nothing has finished executing. We're just deeper and deeper and deeper into things. So the stack is a fixed size, or relatively fixed size, depending on the language we're in, sort of thing when we move forward. All right, now, memory management. In a traditional development environment, very traditional, C, things like that, we don't get the benefit of somebody managing our memory for us. What I mean by that is that we ask for a chunk of memory, we use our chunk of memory, and then when we're done, we're responsible for getting rid of our chunk of memory. Advantages? Extremely fast. Works really well. Okay? We can get lots of memory, we can get lots of throughput, but there's an issue, and it comes down to this sort of piece on the bottom here. All the onus is put on the developer. If you allocate a bunch of stuff and don't get rid of it, it's there forever. More fun, if you get rid of it and didn't mean to, it's gone. It's not there anymore. It's broken. Your program stops working. So while it's extremely fast in the way that most things happen at a low level, it isn't common in object-oriented or in higher-level languages, like let's not call them higher. Let's call them, sort of newer generation languages, to manage memory yourself. It's more common to say, I'd like somebody to take care of that for me and not have to worry about it. Good things, makes development easier. Bad things, somebody has to manage it. The thing is, by the way, is that no matter how smart we write code, it's probably never quite as efficient as having just managed it yourself. It's always going to be a process. It's always going to take guesses. It's always going to be slightly slower. So to that end, we have a concept called managed memory. In managed memory models, we don't ask for memory directly. We go through some type of intermediary. You are now my intermediary. Haha, you are my intermediary. So if I want memory, I ask you, please give me memory. You go find it, you give it to me, I'm able to work with it. But the thing is, by accepting that responsibility, and you didn't know this already, you have to manage all memory that comes through you. You have to figure out when I'm done with it, not me. Okay? You have to figure out when it can go away, not me. Makes my life easier, makes your life a hell of a lot more difficult. There's a lot of things you have to figure out to do that. So when we actually do this, and this is kind of a lie, but that's all right. In Flash Player, we go through a class called GC. The reality is that there's a whole subset here for garbage collection and a whole sub-modules inside of Tamron and what's there. And it actually still bears some of the macromedia names. But let's just call it GC for right now. So in our GC class, we can actually ask for memory. And we can ask for different things about our memory, how much we want to get, and even certain types of memory that we can get. But we ask for this garbage collector to actually ask for our memory and to get our memory, and then we ask for it to manage the responsibility of holding on to that memory and telling us when we're done. Now, for a moment, we have to remove ourselves from Flash Player, or at least from what we think about as Flash Player. When we think about Flash Player, we think about ActionScript code that's running. Okay? But under the hood, obviously, there's a lot more that goes on to make sure our ActionScript code runs. So we got to think about memory being kind of two separate things for a moment. There's unmanaged memory, which is just a big old chunk of memory. It's the traditional programming model. And then there's managed memory, which is the stuff that this garbage collection is going to hold on to. So there's going to be a point in time when something we do in Flash is going to say, okay, we need our first chunk of managed memory. We need this chunk of managed memory now, and we want to manage it, and we're going to want you to take care of it going forward. When we first do this from somewhere unmanaged, somewhere over here in the great unwashed, we reach over and we say we need some chunk of memory. The thing that's returned to me is called, or can be thought of as a root. A root is basically a list or a beginning piece of something that's going to be managed. Now what I mean by that is that once I ask for an initial object, I may then inside that object say, okay, now I'm going to define a property, and now that property has a new object associated with it, et cetera, et cetera, et cetera. But kind of I make this transition. When I first ask for an object standing out here, I don't have anything managed yet. Okay, I've got nothing. So that first thing I ask for gives me back something that's managed. And then every time I ask for something after that, it kind of adds on to that initial piece. All right? But this is really important, especially if you look at any profilers, because you're going to see things called garbage collection roots. And what these are the root level of something the garbage collector is managing. Okay? This is a top-level thing that the garbage collector knows it handed somebody, which then may have something linked to it, and linked to it, and linked to it, and linked to it, all the way down the stack. But this is a root-level thing that the garbage collector knows about. In fact, when we do profiling or when we're trying to find memory leaks, what we're really trying to find our way back to is what those GC roots are. What we really want to do is find out, hey, this thing's stuck in memory and I don't know why. So what I need to do now is I need to work my way back to what the hell is holding on to it and hopefully eventually figure out what the root of that situation is. What's holding on to that, what's holding on to something, so on and so forth. Does that make a degree of sense to everybody? Okay. So something garbage collection knows about, and it's going to be able to deal with it later. So roots are things that garbage collection is managing. It's things that garbage collection are watching. It's things that garbage collection knows how to deal with internally. Now, the thing is, though, the job I gave you so far is pretty easy. Asking for memory is trivial. I can ask for memory all day, and it can give me memory. Where it gets hard is when I need memory back, or when there's reclamation of memory. Reclaiming memory is hard, because we've got to figure out a couple really important things. Well, actually, one really important thing. Is it still being used? And the consequences for freeing a piece of memory that are used are pretty huge. If I have an object, and it's got 7 properties right now, and I'm counting on those 7 properties because I added them, and the next time I run a for loop, 4 of them are missing, that's a problem. That's a big problem, right? Because it's not like we write every line of code to check if every property exists before we use it. It's impractical. So the thing is that garbage collection's got to be really, really sure that you're not using that thing before we actually go forward and get rid of it. So it's going to do that through a number of strategies. Now, I'm going to throw this out here right now so that we can kind of talk about it towards the end. But in general, Flash Player and the way it does this whole garbage collection process is an allocation-based scheme. And that's a 90% truth, especially in newer things. But let's embrace that lie for just a moment. Which is the idea that we have to decide when in the world to go through this process of saying we need to go back and get more memory, okay, or we need to clean up after ourselves. And the strategy that Flash Player generally takes is that we should clean up after ourselves when we need more. What do I mean? I mean that if I allocate 500 objects and then stop and I'm doing nothing else, it really doesn't matter all that much if we ever clean up after ourselves. Those 500 objects can be there forever. No big deal. I've already allocated the memory. They're hanging around. But if I need 501 objects, well, then rather than trying to go get more memory, it might make sense to see if there's anything we can clean up first, anything we can get rid of first, anything we don't need, clean that up, and then reuse some of that memory. Okay? So that's what I mean when I say it's an allocation-based scheme, is that we look for the ability to reclaim stuff before we actually try to go get more. This also means, by the way, number one mistake when we diagnose things like memory leaks or try and figure something out inside the Flash Player is that people say, well, hell, I opened up a process list or a task manager and I'm looking at the amount of memory that Flash Player has and I'm not using these objects anymore and the memory's not going down. Right, it's not going to, because we aren't asking for more at that moment. So in general, Flash Player is going to sit relatively idle. Again, some small lies here, but relatively idle, and not necessarily go through and reclaim that memory. So once we get to a certain point, it's actually pretty rare that we ever go down in memory, at least from the system level perspective, okay, from the outside the flash layer perspective. We'll talk all about the reasons for that too. All right, so some of these things you'll have heard before, but let's clarify some of the lies behind these too. Reference counting. Simplest way, and this can necessarily be thought about as even garbage collection in some ways, but the simplest way that we could possibly imagine to figure out if something is in use is to keep a count. In other words, you go ahead and tell me that I need a pointer or a reference to John here. And what we do is that we keep a count and say, okay, Mike has a reference to John. Pick one more person, we go get a reference to John. Now John has 2 references to him. All right? What does that mean? Well, that means that as long as that reference number is greater than 0, then I probably shouldn't remove John. Because if so, when I try to go access him, he could be gone. When someone else tries to access him, he could be gone. So this is interesting in that it's a really simple scheme, and actually it was the exclusive scheme in Flash Player 7 and before for actually maintaining memory. We only used reference counting. We only actually looked at the number of references that were kept to one thing. And there's good things and bad things about it. In general, it's actually pretty fast. However, as memory grows really, really big, and there's tons of things, which now in Flash apps we use a lot more memory than we used to, it can actually kind of get slow to maintain on every single object in the system. It also, the incrementing and decrementing if needed is okay for certain types of things. In other words, we talk about that heap memory, right? That's really big and it's global and it's out there for a long time. It's probably okay to maintain references on those, and we have this speed. But stack stuff like we talked about, one method calls another method, calls another method, calls another method. That stuff happens really fast. We call one of those, we throw one away. We call another one, we throw one away. They happen very, very quickly. So keeping references and keeping the extra counts on all these things that may only, we may only have a method that's a couple lines of action script, even in bytecode is maybe a dozen lines. Keeping references on all those things just gets expensive. It gets expensive as we go along. It also has a problem called the circular reference problem, and I stole this image from the Tamarin site, and I like it. How many references does this guy have to B? Thank you. 1. And what about the other way? How many references does B have to A? Okay. And if those are the only 2 objects in the system, and we know we only get rid of things that have 0 references, do either of these things ever go away? Okay, which means if we allocate a megabyte for B and a megabyte for A, and these 2 reference each other, but nothing else in the whole system is ever using them, can those 2 disappear with a reference counting scheme? This was part of the problem with Flash Player 7 and before, is that there would be these big chunks of memory that could be stuck forever because we'd create circular references. And of course, they're rarely this simple, right? There may be 26 things that somehow reference each other, but in reality, nothing else can get to them, so they're useless. Because if we think about it and take that term useless again, if nothing else in the system has a reference to A or B, just they have references to each other, there's no way in an object-oriented system I can use those things ever again. Nobody has a reference to them. They're dead. They're out there, but they're still taking up memory. So circular references problems are a big deal. And they're such a big deal that it was the emphasis for saying we need a new scheme to be able to deal with that. And so the new scheme was called Mark and Sweep, or the newer scheme is called Mark and Sweep. Mark and Sweep's not a new thing. It's just a newer implementation. What Mark and Sweep does is Mark and Sweep says, hey, let's start at those GC roots. So going back to this, again, some of the stuff that I actually said was important, believe it or not. Back in the beginning, the GC root, that top level thing we get from garbage collection. What Mark and Sweep says is let me start with that top level piece, one of those roots. And let me literally walk every single property of every single object and work my way down, finding everything, and every time I find something, I'll mark it. Every single time I find this new object, I set a bit saying you're now marked. And then after I mark everything, I can come back through and do what's referred to as sweeping, which is everything that hasn't been marked is unreachable. Okay? There's nothing, again, in an object-oriented system, if we don't have a way to get to something, it doesn't exist for us. So if we walk every object, and what's left, we were never able to get to. And in that case, then, we have found things that can be destroyed. So even that circular reference problem doesn't matter, because if we can't get to A or B, A and B can go away. They can be destroyed. Now, this is great. Mark and sweep takes care of everything. It does a great job for 99% of the time. Actually, Flash Player is a little conservative on this, by the way. And there are times that it actually can't 100% tell. Something could be a reference to something, maybe it's not 100% sure. If it's not 100% sure, by the way, it actually takes a very conservative approach which says, you know what, if I'm not sure, let's leave it there. Because I'd rather leave it there than screw up the program. Interesting thing about this is that it means that Flash Player actually intentionally is creating memory leaks. Very small ones, okay? And not ones that are programmatic leaks. When we create a programmatic leak, we have a problem, right? If we create a leak in our program, it means that every time we execute that code, we're likely creating a new leak, which add up quickly. These are like small things. It might leave an array here, it might leave a string here, something like that. They're relatively small and they're relatively random compared to the things that we do in the program. But nonetheless, there are little things that will potentially leak if Flash Player is not sure about them. It's very, very conservative because it doesn't want to have anybody have a program which is suddenly missing an object they expected to be there. Here's the thing. Mark and sweep is dreadfully slow. In fact, actually, the dreadfully slow part is the marking. If you might imagine, if you had to walk through, a family tree and mark every single thing all the way went down from the beginning of time on, which is basically what Flash Player does, it's really slow to work through every one of those possibilities, to work through every piece and mark every one of them. And so while mark and sweep is absolutely fantastic and will always catch what we want to, it becomes an issue. Turns out some people like their content to play back relatively quickly in Flash Player without giant pauses. So the strategy is that there's a hybridization between these two and some more rules in there and a missing G, but we won't count that one. First of all, we use mark and sweep in something we're going to talk about in a moment called deferred reference counting. What that means is that if we could take advantage of the faster reference counting and the slower mark and sweep, and we kind of do those together, then we could actually get to the point where we have something that's maybe fast enough but also thorough. More so, though, if you remember, reference counting still takes a lot of work to maintain bits and changes and pieces like that inside an individual stack. So we actually have something called deferred reference counting. And deferred reference counting only counts things that are actually on the heap. It does not count things that are on the stack. So that means the things that are changing very, very quickly and constantly inside of your functions, those aren't counted. Reference counting never looks at those. But the things that are globally defined, the things that come from the heap, Flash Player actually does reference count. Okay? So we have heap and stack, and we separate those two as far as reference counting goes in order to make things even faster. And again, this all comes down to the fact that since we're not allocating memory ourselves, because by the way, again, if we were allocating memory ourselves, none of this would be a problem. It's only a problem because we don't want to have to take the responsibility for doing that, which means someone has to. But if somebody has to take time to do it. And the way that Flash Player works right now, that means that if I actually use a bunch of memory and someone has to take time to do it, it's going to necessarily pause our playback. It's going to necessarily mean that we're going to miss a frame. Well, maybe not miss a frame, but we're going to elongate a frame. We're going to slow something down. At some point, this work needs to happen. All right, so the optimization is, say, count the heap, don't count the stack. Thing is, that potentially leads to another problem. So we have something called a zero count table. What a zero count table is it's a table that we move all objects to when we don't have any more reference counts to them. So we remove all pointers to John. John's now eligible to be able to move off into the zero count table. And this zero count table is basically, you could think of it as like a waiting room for execution. Right? Everyone goes in, you wait, nobody really comes out. It's a waiting room. Thing is, though, is that we're only counting things on the heap. Remember, we're only reference counting those. We're not doing anything on the stack. So there's a problem. If I see John as having 0 references to him at this point and I move him and he's ready to go, if I just deleted him, turns out I could have had 25 references to him somewhere on the stack because we aren't counting those. And suddenly now we have a scenario where I've destroyed John ruthlessly, and unfortunately, there's still programs somewhere that wanted to access him. So instead what happens is that there's this waiting room. John moves into the zero count table. he's over there, which means that all the stack references can still access him. And what really happens is that we go through and we check the stack completely. And once we're confident that he's at 0 references and there's nothing for him left in the stack, then we can actually turn around and we can destroy John. John, you're dead. You've been ruthlessly garbage collected. Okay, so that's the 0 count table. That's why it exists. Now, here's another problem. So I mentioned, especially the process of marking in garbage collection is not a fast process. Okay? So we can't do that all at once. Well, we could do it all at once, but we get noticeable pauses, right? So we don't want to suddenly go off and process this whole garbage collection scenario at once, or we'll get a noticeable pause. We'll get something that's a problem. So garbage collection actually happens incrementally. It doesn't happen all at once in Flash Player. This also leads to a bunch of other confusion, right? Potentially, why is my object, when does my object disappear? Why is it still here? All these sorts of different things that may exist when we're looking through Flash Player. And in fact, if you're familiar with any of the profiling tools, it's the reason that we can generally trigger full garbage collection inside of profiling tools is to give us a better sense of what things would really look like. Because for our perspective, this isn't true, of course, but from our perspective, the way in which Flash Player is going to decide when our object goes is almost non-deterministic. Okay? From our perspective inside of ActionScript. At some point, based on workload and queue and number of objects and things like that, Flash Player is going to get rid of it. And incidentally, all of this marking time, all of this time to do things that we need to, is actually very much related to the size of the memory we have. It's proportionate. Which means the bigger our application is, the more code that we have, the more assets even that we actually have, the longer it takes to actually go through the sweeping process. So this becomes more and more important as time goes on. So instead of actually going through and doing everything in all one step, there's a queue, and it's called the work queue. What happens is that every one of those garbage collection routes is shoved onto the work queue. Okay? It's put onto a work queue, and that work queue then actually is sort of the list of things that garbage collection needs to go through. And then, as time is available, that queue is going to be processed a bit at a time. Incidentally, this is probably an interesting time to talk about this for a moment. In the allocation part of it, we don't actually just get memory from an operating system, from Flash Player, okay? When we actually say new giant object, we're asking Flash Player for some memory. But Flash Player has to get it from somewhere. And it actually gets it from the operating system. In some cases, depending on the operating system, it actually gets it from a virtual pool from the operating system. I'll explain that in a second. But what happens is that we actually allocate memory from the operating system, and then we dole it out internally. So when we go ask for memory from the operating system, it's actually an expensive operation. It takes time to do that, a lot of time. So we don't do it a little bit at a time. It would suck. It sucks up tons of time. In fact, what we do is that we minimally go out there and say, hey, give me like 16 megabytes. Give me that chunk of memory right now, and then we manage the rest of it internally. See, it sucks to go out and actually ask the OS over and over again for more memory. And then we have to deal with slower things because of fragmentation and other issues because the memory may not be cohesive or rather continuous. So we ask for like 16 meg, and then we dole it out into pages, little 4K pages at a time that Flash Player keeps track of. And so what we're trying to do when we do garbage collection is we're actually trying to clean up these pages and we're trying to clean up this memory because, again, I mentioned it was an allocation-based model. So if you think about it from a certain perspective, what we're really trying to do is, whenever possible, we're trying to make sure we don't have to go back out to the operating system again. So the strategy is do whatever you can to make sure we don't go out to the operating system again because that's going to take a lot of time. Okay? So this whole strategy is about trying to take care of balancing these things. So this garbage collection route, meaning everything we initially asked for from an unmanaged perspective, are all pushed onto this work queue. This work queue is then managed by the garbage collector. It starts moving through this work queue in order to do things. Thing is, though, is that processing this queue takes time. And what I mean by time here is that in Flash's perspective, over n frames. Maybe over n minutes, depending on how things actually work. And, well, it leads to an issue. because I could be touching some of those objects. In other words, I could do part of garbage collection, part of this queue working, and then some ActionScript code runs. And then I'm going to do some more GC, and then some ActionScript code runs, and then some more. So how do I make sure that each time I'm not actually screwing or changing the results of what actually had just been done in GC? And this becomes a problem because of the incremental nature of things. So there's actually an interesting thing here which we'll talk through, and it's called a Tricolor algorithm. What happens is that for each bit or each GC route that is worked through, Flash Player sort of assigns these three colors, okay? They're really states to things. Black means that we've actually marked this thing and we don't have any more work to do on it. This item is done. We've gone through this whole GC route. Gray means it's in the queue. It's here. We haven't marked it yet. And a white object is an object that's not in the queue at all. All right, so our three states, we've done it, we know about it and we're going to do it, or we don't even know about it yet. Now these three states, again, are help us manage that situation where things are changing as we're working through. So when we first push things onto a queue, they're all gray. Okay, so every item from the GC route we push onto the queue is gray. Why? Gray means it's queued, but no work has been done yet. Then we start working through them in a given frame. As soon as we've worked through an object, it becomes black. All right? Any white objects are going to now be added to the queue. Those become gray. So our transition is always white to gray to black, white to gray to black. All right? Now, this one little line here, which encompasses an impossible amount of code, is the really important part. If I have an object, and John, you're back and you're alive again. John is here, and John has been marked, and it looks as though John is been ready to go. He's been marked. He's already been figured out as far as how garbage collection is going to go down. And now we have to pause to run some more ActionScript code. But I walk over and I hand John a reference to another object in the room. Well, I've handed John a reference to another object, which means John's marked black as though he's already been taken care of, but now there's this other object that he has a reference to. Kind of invalidates the situation. Maybe that thing has to actually be gone through. Maybe that thing has to be collected. Maybe that thing has to change. So there's this whole concept of write blocking inside of Flash Player, which actually means that every time we write to an object, Flash Player does checks like this to figure out, well, what are we writing to and what state is it in? And if it so happens that I give John a reference to something and John is already black, then that new thing that I just gave to John has to also be thrown on the work queue. So this work queue is a very, very evolving thing because every time we touch code, it potentially alters the work queue, adds more to the work queue because something runs, we run. The GC runs, we run. So since we're interactive with each other, the only way to make sure that everything goes through is to watch every single thing that's written. Does that make sense? Liars. All right, who wants to tell me that it doesn't make sense? All right, why don't you ask me a question and we'll go from there.
What's confusing is, from what I understand, a black object is something that's garbage collected. It's destroyed.
Great question. A black object's not something that's garbage collected. A black object is something that's been marked. Okay. In other words, we've actually moved through the process of having already gone through that object and marked and did what we were supposed to. Okay? The thing is now is that we might be adding something to something that's already marked.
Like an event listener or something like that.
Something happened to something that's already marked.
So if John, say, is marked, you can't really externally assign some new object to him because you don't have reference to him.
No, he's marked. He's not collected. So in other words, marked means he's actually still in the system. Right?
If you mark him, it means there are no references to him.
Marking him means there is a reference to him in this case.
Oh,
okay? So there is a reference to him. We're not going to sweep him up. But the thing is, in this case, right, is that we marked him, but now I'm screwing with him right after we just marked him. So the things I did after that, who knows what's actually going to happen there. Okay? And that comes into an interesting concept, too, which we'll talk about, which is what weak references actually mean in all this, too, and how that comes together. Okay? So we need to track, basically, every change and modification that happens to these objects that have already been marked, or we're in a situation, potentially, that we aren't doing as thorough of a job as possible, and we don't actually collect things. By the way, the only situation that's actually worried about here is this one. the change of adding something white to something that's black. Because if you add something gray to something that's black, well, it's already on the queue, so we know we're going to process that. If you add something black to something that's black, it's already been marked anyway. We're cool. And every other sort of combination that might happen. If you add something black to something that's white, well, the white thing's not even on the queue yet. It will be soon, yada, yada, yada. So every other combination's covered. But it's this evil one right here that causes problems, and it's so this one that they're really looking out for at all times. Does that help clarify? Yeah?
Is Flash Player unique in this whole process, how conservative it is, or are there other things related to it?
It's not. Yeah, I mean, none of these algorithms are necessarily Flash Player specific. Okay, all of these things exist in computer science, but it is very conservative. It takes a very conservative approach compared to some other systems. Mainly, and there's some little bit of weirdness in the way memory gets stored and where it can't necessarily tell if it's a reference to something or like a number. That's a little bit unique. But for the most part, this is pretty similar to how a lot of other virtual machines work. By the way, anyone who's really bored, you can still go read all the source code. Because all of this stuff that's here is actually available in Tamarind. You can go read all the C++ if you're so inclined. Everyone downloading that right now? All right. Okay, so we're going to talk about this really quickly, and then I'm going to jump back here. What's interesting about this, actually, you know what? I'm going to put this on hold for a second, and then we'll talk about this. Everyone's heard of a weak reference, right? Okay, who wants to explain it to me? Great, everyone just says, comma, true. That's fantastic.
You put a listener on something, and you want it so that if there's only a weak reference, a weak event listener on it, then you'll GC it.
Okay. So that's a practical, so what we basically said was that if you put a weak listener on something, okay, then if there's only weak listeners, you can GC it. And that's true. Another way, though, to actually think about this, now that you kind of understand the mark and sweep of what's going on, is that normally when we mark, we follow all paths, right? So I go from this object, and I follow every single path to every other object, and then every single path to every other object. But when I actually get to something that is a weak reference, I can't follow that path. The garbage collector can't pass down that road for something that's weak. So in your example, if I have the stage and I add a reference or an event listener and it's a strong reference, well then when I get to that one, I'm going to follow that down and I'm going to get to the object that's listening, right? If it's weak, I'm not allowed to take that road. The garbage collector can't follow that path, which means it never gets to that object to mark it. So that's what's really happening when we talk about weak references, is that we're blocking the garbage collector from evaluating that path, which means when it evaluates what's actually out there to get rid of it, that one can't be considered because the garbage collector can't follow it. Get me? Okay? Incidentally, that brings up another point here, which is something interesting about event listeners. And by the way, event listeners are one place we can use weak references. What's another place we can use weak reference in Flash? Dictionary. And is everything about the dictionary weak? Not everyone at once. It's overwhelming. The keys. Who's at it? There. Yes. The dictionary's keys are weak. Okay? So not the values of the dictionary, the keys. Okay, the things we store as keys into the dictionary are weak, which again means that a dictionary that's set to weak, none of those paths can be evaluated by the garbage collector. None of them can be gone through and found. Okay? That's why the dictionary is actually slightly complicated in the way that it works, because the dictionary is an object with a lot of extra logic because it actually has to account for the fact that when it goes and knows how many keys and stuff it had last time, some of those may not exist anymore. Some of those may have been ruthlessly killed like John and are gone. And that key was there a moment ago, but now it's gone because it treats them as weak. Okay, so going back one other second here, which is important, when we add an event listener to something, and I know this is said a lot, but I think it's really important to keep in mind. If I add an event listener to John, that means John has a reference to me. Okay? Works the opposite of what we normally think about it, and this is really important for the thing that you just said, too. If I add an event listener to John, it means that John needs to call a method on my object when something happens, which means John needs to know where the hell I'm at. I don't need to know where John's at anymore. It doesn't matter. But John forevermore needs to know where I'm at, right? To notify me, which is, by the way, why event listeners to global objects are the #1 way to write memory leaks inside a Flash player. Because now, John, you just became a singleton. You've just, yeah. Yeah. So now John's a singleton. John's a singleton, which means he never goes away, right? After he's created, there's a static variable that points to him, and that never gets collected. It's there forever and ever and ever, which means I'm a lowly button on the stage or I've been added somewhere. And the moment I add an event listener to John, John has a reference to me, which means you remove me, you get rid of all other references in the world to me, you destroy me, you attempt to light me on fire, you do whatever you want, but I stay around forever because John knows who I'm at. You have no way to ever find me again, but John does. And that means that I have to stay in memory forever. That's the number one cause of memory leaks inside a Flash player, is not understanding that relationship. That's why weak event listeners are so important and a little scary, because it means that, hey, I'm gonna go ahead and add a listener to John, and John's going to keep a reference to me. But we won't consider this one for garbage collection, which means if everyone else forgets who I am and the only person is John, and there's a weak reference here, garbage collection can't find me through him, I'm good to be collected. That's why weak event listeners are so very important to global stuff. Now, why are weak event listeners bad? Because things can get collected. What was that, John? Because weak event listeners mean that I'm going to potentially be eligible for garbage collection all the time, right? If anything else removes me. So, for instance, let's say I have an object, and maybe I have a timer, or maybe I do something like I register an enter stage or enter frame event on John. Now you're going the other way, right? So John goes off and he says, hey, notify me every time that there's an enter frame. And then he's going to go do his stuff, and nobody else has a reference to him. And he made that reference to the stage weak. Well, at some point, he's going to disappear. Same thing with like a timer or other things. If I've got the only references to me are weak, I can disappear, right? Which also means that if you're going to do things like weak references, you better manage what you're doing, because at some point, the garbage collection can just rip that out of memory. Happens all the time. You have something that's firing on some type of like enter frame, and then suddenly it stops firing. Why? Well, because garbage collection got to it, because you set it to weak. I bring that up, by the way, because of the fact that so many times I hear things like, well, just make all event listeners weak. Okay, I am not for absolutes. All right? It is not an absolute world. I'm all for you knowing what the hell that means and deciding when you should use weak and when you shouldn't. And the reality is you need to use weak when you don't want that evaluated, and you need to use strong when you do. All right? Your number one recourse, by the way, with event listeners is not to make everything weak. It's to remove all the event listeners that you added. Right? Because then that link between us is severed, everything is cool. Weak event listeners are fantastic in scenarios where I may not have the ability to remove it, or I may not know when to remove it, or any other number of things. But it's not like a simply, hey, just always set this flag and everything's good. In fact, it can cause more problems than it actually helps. Get it?
Along those lines, you find the strategy of creating a destroy method that always gets called whenever something is removed. Do you think that's either a code smell or a good strategy for
it's a. So the question was, is it good to have like a destroy method which always gets called? The first problem is, how do you guarantee it always gets called, right? And that's the problem here, is that in Flash, we have to call that destroy method. We have to call that destroy method manually, which to me scares me just a little bit, because it gives a false sense of security. Because I go and create this destroy method, and that's real nice, but now let's say I register myself as an item renderer, and I have some class that's an item renderer, and now a list component somewhere is responsible for creating and destroying me. Is it going to call my destroy method? No, it's never going to do anything, which just only worries me because it's that sort of false sense of security that now I've got something that's actually covering me when I really don't. So in general, if you have an object which actually has complex setup, I don't have the problem with having a teardown, whether it's destroy or something else to do that. But again, it's not a language where we have this concept of finalization for us. So we have to know that we're going to call it ourselves, and we just got to make sure that doesn't become a crutch for doing things. So yeah, unfortunately, there's not a good answer for that one. It is what it is. Incidentally, finalized objects, just for those of you who don't know, which is something that's supported internally to Flash Player, just not exposed to us, are objects that have a method called when they're about to be destroyed. Okay? And in fact, incidentally, under the hood, that's how reference counting is actually implemented. All right? And that's why reference counting is a lot faster, is that when I add a reference to you, you get references added. When you decrement your reference, what actually happens in the traditional model is that when you get to the last one, when you're at a 0, you would actually destroy yourself. It would happen immediately. It doesn't go through some big asynchronous process like garbage collection would be. That's how the traditional model works. Okay, does all that make sense? To some degree, at least?
Slowly.
All right, it's a good start. All right, so Flash Player Incubator introduces this new API in Flash System, and it's kind of cool. It's the start of some good stuff. It's also a really descriptive and long method name, which may or may not stay the same as it comes together. Pause for GC if collection imminent. All right? I mentioned that one of the problems with garbage collection in general is that the system's always trying to figure out, when do I garbage collect? How do I make this most optimal? How do I do these things? And in traditional systems, we don't actually have that, right? In a very traditional system, we instead have the scenario where we tell it specifically now free. Well, there's approximately 0% chance that we're ever going to have an API inside a Flash Player that says, I'm really done with this object, you can destroy it. True or false, the overriding theme behind the Flash engineering team is that we don't have enough context to really know when something can be destroyed, and the consequences of destroying something that shouldn't have been destroyed are much worse than the possible consequences of creating this leak or doing something. That's actually fairly reasonable. But what they're beginning to do is do little things like this, which are interesting, which are give us the capability of maybe indicating that it's good time right now to run garbage collection. It's a really good time for us to go out there and do some work. Maybe, for instance, I made a server call, and I know that that server call is asynchronous, and it's going to take a little bit, a quarter or a half second before it gets back. That's tons of time in the garbage collection world. So I can actually tell the garbage collector, hey, now is actually a really good time to go and to do garbage collection for me. Do what you can, and do it now. Conversely, I can also tell it the other side, which is, I'm actually about to play an animation, or I'm about to do this, and it's a really, really bad time to go do garbage collection. So it does not actually necessarily guarantee something is not going to run. It influences what can or can't run. So what happens is that we advise, and that's why this is actually called GC advice. We advise the GC that it's a good time or a bad time to do different things. In fact, as a start point, the GC, if it's in the middle of a cycle, will always actually finish the cycle it's in. But if you remember, our cycle is kind of these work queue things, right? So if we tell it that it's a really good time to go do garbage collection, it might do more of its work queue than it would have normally done before it bailed out and went back to our code. All right, to tell it a little bit more. And by the way, when the API for this is that we actually pass it a number, and that number is kind of a ratio, kind of saying, hey, it's a better time or it's a worse time. It's a ratio. If there's no GC ongoing, okay, and we actually tell it, hey, this is a good time, it actually may start. It may start, and again, may is the key word here. We're not getting complete control. We're advising the garbage collector what's going on. So it may be started if the budget criterion is met. And what they mean by this is that, again, we're going to give it a ratio. We're going to say, hey, now is a better time, and it's going to look at it and say, well, I know you told me it's a better time, but reality is I'm actually seeing what our frame rate is, and I'm seeing the system processes, and I'm seeing how much work I have to do, and it's really not a good time for me. But we're influencing it. More specifically, if we tell it it's a really good time, the allocation budget will not be reduced. Okay? So meaning that we have a certain amount of time that we're working towards allocating, we're working towards working through things. We're not going to reduce that amount of time at all in any capacity, even if it seems to be taking us slightly longer. We'll still go through and do that, and it is in fact possible that we may increase it. So this is actually the first of many things that are coming as far as the GC collection imminent. Well, theoretically coming. To be honest, a lot of that, this is an incubator, but a lot of those things are derived from what seems to be going on in Xamarin, which seems to relate back to Flash Player. So it might be a little bit like reading tea leaves. But there seem to be a lot of changes to the way the garbage collection is working and coming to make things more efficient. Okay, so on that note, I'm going to go ahead and pause because we're running out of time on questions. Questions? Anyone still alive enough to answer? Yeah, back there.
Best tools for memory and profiling, so you know when you're running into a situation where you have to start considering these.
Yeah, that's a great question. I wish I had a great answer. Why are you doing ActionScript directly, Flex? What are you doing?
ActionScript 3 and the Flash Pro.
Yeah, I mean, the tools are somewhat limited, which you can use. Talk to me afterwards, and I'll point you to a couple things that I go through. But the profiler that is out there, and more specifically, which is interesting, is and I should mention this, is that there's not only the profilers which Flash and Flex now allow us access to, but those APIs which the profilers call or talk to are actually in Flash Player. Okay, so there's actually all these profiling pieces in the debug version of Flash Player, and we can actually write stuff ourselves. So it's actually sometimes interesting. If you really get stuck on a piece, you can actually save information off from the profiler all by yourself, and what objects are still in memory, what got collected, what didn't, trace it out, or set it. Even I have one that even sets it to a local shared object. And actually, I sometimes find that to be even more effective in very narrow circumstances than the tool. The problem with the tool is, again, they're trying to automate for us, which means that we may very well start something and go through and get hundreds, if not hundreds of thousands of objects that it's all tracing the memory out for, and really there was one little section over here that we cared about. So sometimes I actually use the APIs directly myself and prefer those in some ways. Fair enough?
There's times you manually run system, I mean, literally system.gc does the method.
So system.gc is an interesting thing. In certain circumstances, when it feels like it, it will do something for you. Most of the time it won't, and certainly not in production. It's almost a no-op in production. It almost does nothing for you. There are some tricks. Grant Skinner has one that everyone's probably seen where you actually cause an error, and that error forces garbage collection to happen. But actually, and it's different between AIR, by the way, and Flash. There's a difference here. In AIR, it does more. But in Flash, generally in production, calling system.gc does almost nothing for you.
But there is a difference in AIR, because that's where I use it, and it saved my file.
Yes. In AIR, you actually are doing something. In Flash Player, you're not necessarily. And that's because there's a difference in the system model and everything goes. Incidentally, I'm going to finish up, but last thing on this, the side note, with that whole scenario, is that the whole calling garbage collection thing, and the reason it's so complicated, is because of the fact that we're trying to balance two things. If we overly garbage collect, we slow down the system, right? But we keep really narrow memory profile. If we don't garbage collect enough or often enough, though, somebody who's allocating tons and tons of memory may actually be able to allocate faster than we GC. So it's the balance between those that it's always trying to strike. And reason I like things like this advice and things that are coming is that I know better what I'm planning on doing than the system knows. The system may have known what I've done, okay, but that's trying to guess information on my past behavior. I know what I'm about to do. So that's why these things are kind of cool. All right, so before they lynch me, I'm leaving. Thanks, everyone.